Okay, so let me do it again. So it's my great pleasure to introduce Mr. Jules Damji. He's a lead developer advocate at Anyscale and an MLflow contributor and co-author of Learning Spark second edition. That is the Bible of Spark. And also he worked at many leading companies, especially the leading big data companies such as Hortonworks and Databricks that dominate the market of big data and distributed parallel computing system. And now he works at Anyscale, that is to achieve large-scale distributed parallel computing for a lot of businesses. And also he went to Oregon State University, and clearly he also is an alumni of California State Systems. And so please give a big hands to Mr. Jules Damji. And Mr. Damji, can you start your talk?
Okay, well, thanks a lot, Jongwook, for that very illustrative and flattering introduction. I'm delighted to be an alumni of Cal State and delighted to be in front of you graduate students of MBA class of 2022. As Jongwook pointed out, I knew him from early days where he became an advocate for Apache Spark, and he has actually given a lot of talks at Data Plus AI Summit. And so it's really a pleasure for me to be here to share some of the things that we have actually discovered over the period of years. So today's topic I've titled The Future of Distributed Computing. What does it actually mean? Where it evolved, how it evolved, and scaling AI workloads. And just, well, I mean, you already got an introduction, so I'm going to skip over this particular slide. So who are we? I mean, I work for the company who is the original creators of Ray, and this was sort of a distributed system that emerged out of Berkeley Rice Lab. It's the same research lab when Apache Spark evolved as well. And what do we do as a company? We sort of provide, the managed service to Ray, to run Ray in a public cloud, so you don't have to manage it. And we want to scale all the AI workloads because that's what the future is today. And then why do we do it? We want to make sure that everybody, you don't have to be a systems engineer, you don't have to be a distributed programming expert to learn how to distribute computing. So that's our mission, and that's why you actually want to do it. So today's talk, the way I've sort of structured it is I want to sort of, give you a history of the evolution of distributed and cloud computing, right? Because it's actually very, very important to have that particular preface to make the case that distributed computing now is going to be a necessity and not a norm. And we have sort of entered the zeitgeist of machine learning and AI. And today, that notion and that paradigm is an imperative. And it used to be the case in the early days where it was more of an exception. And today now it's become a necessity. And then we'll jump into why we feel Ray, what is Ray and how Ray fits into this grand scheme of things. And today, what is it about developers who actually are looking for to do distributed computing? And then throughout this, I'll pose for Q&A. If you have any questions, I'll answer it. I want to make this more interactive because I don't want it to be sitting over here and proselytizing things and giving a lecture. I like this to be sort of more interactive thing. And that's the nature of how I interact and communicate. So the future of computing is distributed, as I say, and why that is the case. So let's actually look at the evolution of how actually distributed systems evolve. And it's not something new, right? It has sort of been with us from very early years, where if you look at in the 1990s, since the 70s, ARPANET was the inception of distributed computing, right? We had people sort of communicating over the ARPANET to connect to the mainframes, and that sort of led to the evolution of the email, where Ray Tomlinson in 1971 actually created the distributed system, and that's where we started writing emails in this very archaic form. So that was the 1970s, and then if you go 10 years ahead, we had the emergence of high performance computing, HPC, And this was a research effort led by National Science Foundation and some of the 5 universities, where we actually had very high performance computing that people actually connected, and they were using very heavy loads. They were doing, weather forecasting. They were doing molecular modeling, structuring. They were doing all kinds of stuff that required a heavy workload. And this was sort of the dedicated part of the 1980s. And then 10 years on, we saw the emergence of the internet, where it actually started initially at University of Alabama, where they actually released Mosaic, which was the first web browser, which then became Netscape. And it was a company that I joined from very early years. And I actually have a little proof to show you. Yeah? This, I don't know how many of you actually remember this particular navigator, which was the Netscape browser. So it sort of dates me how long I go to the early years. But that sort of was the new era of the 1980s, where web became the de facto how people communicated. And as a result of that, we had the flourishing of websites, and Amazon was one of them. And a lot of websites sort of emerged over the years. And then if we move the clock forward 10 more years, we saw the emergence of Google, right? Google now entered the era of big data. And when you talk about big data in the 2000 knots, you associate big data with scale, and you associate scale with Google. And they sort of released this whole idea about how you actually do distributed computing using the Mapreduce paradigm, where you actually have parallel tasks which actually run, and they come out and do some reduction, and that sort of led to the big data. But what really emerged in that particular early years was the 2 papers they actually released to the academic. One was the Mapreduce paradigm, which allows people to do parallel computing on data and reducing fate. That was the first part of it. And they also released a paper called the Google File System, which was built on Bigtable. And that sort of led to what I call the new era of Hadoop and Spark, because the big data, how you actually distribute and how you compute the system, sort of led to the early years of where Hadoop, companies like Cloudera and Hortonworks sort of came up with the idea of Hadoop and made it open source, which eventually led to the foundation of Spark. And now today we have this emergence of all this data that has been accumulated and has been fed into data warehouses or data lake or lake houses. And the problem is what do you do? What do you do with all this data that you actually accumulated, right? And if you summarize the generation of these cluster UJET, it started with MPI. MPI stands for Message Passing Interface. A lot of people actually wrote a lot of spaghetti code. And then if you go into the knots of 2000, that's where Apache Hadoop and Spark actually came into the prominence, where the paradigm was you were doing massive parallel tasks happening in parallel because you had independence of data. There was no dependency of data. And then you had the Mapreduce thing. And then if you move the clock forward today to 2012 and in this new decade, the paradigm is slightly different. The paradigm now is that you have the emergence of machine learning and deep learning that requires not necessarily using clusters, but they require a lot of point-to-point communication. So each and every clusters are talking to each other. And that has sort of led to this new frameworks such as Ray and PyTorch and TensorFlow that require you to scale your workloads at a very high load. And so the question is, I have all this data that I've accumulated over a period of years, and I have put this in my lakehouse, which is now sort of the new preferred way of putting your structured and unstructured data, and then using machine learning frameworks to go ahead and do processing and scaling. So how do you actually do that? And before we actually talk about scaling workloads, we also have to somehow think about how the evolution and the trend of cloud computing now today has actually played a huge role in scaling out and doing data processing at a massive scale, both machine learning as well as doing in ETL. So I think it's important to have that context too. So there are 2 fundamental things. One is the evolution of high performance computing or distributed computing. But then in parallel, what really enabled to be able to do that at scale is the evolution of cloud computing. So I think that's very important. And I think the whole idea is to understand, how it actually fits into the grand scheme of things. And these are some of the slides that I actually borrowed from my very esteemed colleague, an old community friend, Paco Nathan, who actually gave these lectures both at the Ray Summit and also at other conferences. But the whole idea is that, what do you do when you have an application which is really, really too big, right? It's too complex to compute, and it's hard to fit in one server. So what do you do at this point? Now, there are a couple of options. There are a couple of routes that you can actually adopt. And one is that like in early days, you take a massive big computer that had lots of CPUs and you scale up vertically. So that's the whole idea about scaling up, where you have one big machine and you put everything on it and let it just crunch away all the data and all the analytics that you actually want to do. That sort of scaling up kind of makes sense. The other notion and the other option is that what you do is you divide up all the little chunks of data that you have and little computes that you actually have, or little functions and whatever that you want to compute your data on, and distribute it across the large cluster, right? And that's sort of scaling horizontally out. And today's trend is more favorable in scaling horizontally out, because you can actually sort of take advantage of cheap hardware, you can take advantage of cheap compute because of these, and cloud plays an enormous role into that. And if you look at the histories of how some of the emerging technologies that I showed earlier from 70s to 80s to 20s to not have emerged, those are the exemplary and those are the examples of the MPI, the Hadoop, and the Spark, and recently most Dask and Ray, that sort of use this paradigm to scale things out. But an important notion of scaling things out in a distributed manner, there are trade-offs, right? There are trade-offs because you have to understand the risks and you have to understand the costs. And the risks manifests itself in a couple of ways when you're doing computing at scale in a distributed manner. One is, what about we have divided this particular chunks of data across your cluster, and you have some sort of a synchronization error where you have inconsistency data sitting in one partition and data sitting in a different partition, which are not consistent. And now you're stuck with the idea of what we call in the computer paradigm, split brain paradigm, where you're not sure which data is right and which data is wrong and which one should you use. So there's like the split brain effect. The other risk is obviously, what about if you have one of the servers in the cluster goes down and you have data associated with the cluster? What happens? Do I actually have to do the compute? So there is a lot of complexity involved in there, and there's a lot of synchronization. And so this distributed computing becomes a challenge, and you have to somehow encompass this, and you have to accommodate that for those risks and mitigate those so that it's a lot easier for you to do that. And so what actually happened was that this led to the whole idea of cloud computing, arguably was the embodiment of distributed system. And then because of the cloud computing, companies like Amazon, who were the first one the past 6 years, gave us the ability to scale things up horizontally, because the JVMs would be cheap, and you can just spin up an EC2 cluster on any of these machines, or whether it's cloud, whether it's Amazon or whether it's Google or it's Microsoft Azure. So that was sort of the initial impetus that actually led to the whole cloud computing. Now, there are a couple of articles that I want to point out to, which sort of played very much a role in defining how cloud computing emerged. And this particular blog post was written by esteemed Professor Ian Stoica and David Patterson. Ian Stoica happens to be the person who was also co-founded Databricks, and is also one of our co-founders at Anyscale. And they were actually working with the students in Berkeley at that time. This is 2009, and cloud computing emerged, AWS, in 2006 or somewhere around that time. And they wanted to define the formal definition of what cloud computing is going to look like. They were trying to figure out, how do you actually formalize certain design pattern that's going to emerge. And the result of that particular work in 2000 actually was quite fruitful. There were about 17,000 citations across the academic and also across blogs about referring to what Berkeley thinks cloud computing is simplified, and what's going to be where the trends are emerging in 2009. And that paper, or that particular blog, was actually very prescient in predicting, how cloud computing is going to emerge. And there was another follow paper about 10 years ago, which somehow redefined what cloud computing is. And I think this is something that I wanted to point out, 10 years on, in 2009 at Berkeley, this was the initial paper that somehow defined pretty much what the view of cloud computing is. And they actually provided and defined certain design patterns. And design patterns in cloud computing is how people in the industry as well as in the academic are building distributed systems so you can actually do big data analytics at scale. And they provided a formal language to describe certain patterns. And if you look at the pattern over here, these are kinds of little architectures that define the cloud computing, how somebody is doing stateful component, or how somebody is doing a Mapreduce Paradigm, or how somebody is actually doing distributed computing in this particular manner. So that was a formal language. And a result of this, a lot of work that actually went into this particular paper was also a forebear in the emergence of what I call the Apache Spark. And at that time, the original founders of Databricks, Michael Ambrust and Diane Stoica and Reynolds and Ali, all were part of the MLab at that time that sort of gave the emergence of Spark. And interestingly, 10 years after that, right, a very notable postdoc graduate at UC Berkeley called Eric Jonas, who was now working at RISE Lab. And RISE Lab stands for Research Intensive and Simplified Version of the new lab that emerged from MLab. And he came up with a paper along with his colleagues over there to figure out where in the next few years cloud computing is going. Where are the big data analytics actually emerging? And there were a couple of observations that actually he made. He realized that all his students in the RISE lab at that time were not using Spark. They were using machine language, but they were all doing that on their laptop. And they were trying to figure out why is it that they're not using Spark. And it turned out there were a couple of things that actually people wanted to do. And one of the observations was that they wanted to use everything on the laptop and then be able to compute something on the cluster right away. And they didn't have to worry about pre-allocating the cluster resources. They just wanted to connect to it and say, here's my job, run it, right? And I think one of the three observations that actually emerged out of that were pretty much defined how serverless computing is going to emerge over the years today, is this whole idea about decoupling of computation away from storage. Because if you look at, for example, S3, or if you look at the EC2, they scale independently. And as a result of independently, you can sort of somehow decouple that, right? So you don't have to have this idea, the old idea of, I'm going to allocate a computer. Now I have a computer running and I'm just going to run my job on it. This abstraction allowed people to just write particular code. And then when they need to compute to a larger scale, they just submit it to a particular cluster. And the cluster will figure out how many compute resources that I need to figure out. Oh, this compute is going to use a graphic processing unit. So I'm going to have it create a cluster with GPU. And then you only pay for the amount of CPU and the GPU and the storage you need. And there was this whole idea about serverless computing. And that somehow fed very much into this whole idea about what Ray is and how Ray became sort of an important part as an emergence of this particular trend now happening, where people want to be able to run things on the laptop. And when they want to scale something on the internet, and they want to scale something at a large scale, they just talk to the particular cluster and let the cluster figure out how am I going to compute, let the cluster figure out how I'm going to deal with fault tolerance, let the cluster figure out how I'm going to scale and scale down as the need of the data processing or the machine learning workloads emerge. So that sort of was a lot of feedback into emergence of Ray. So let's now move into what's Ray and why Ray. Now, before we actually move into it, I just want to pause here for a couple of seconds and ask if anybody actually has a question about how I sort of describe the emergence and the evolution of both distributed computing as a necessity and the evolution of cloud computing and how it actually plays today and where it's actually going. Do you guys have any questions?
No.
Okay, brilliant. So let's move on then. So what is Ray and why Ray now sort of fits into this new era of machine learning. And undeniably, I think I would contest that we have sort of entered what I would call the zeitgeist of machine learning at massive scale. We have entered that particular era. And why is it, right? One reason is that machine learning has become very pervasive. So there are three trends that the original creators of Ray, Robert Nishira, Ein Stoica, and Philip Moritz, who were PhD students of Jan Stoica at Rice Lab in Berkeley, observed three trends which were actually happening that sort of somehow defined. And they realized that machine learning has become pervasive. It's become so pervasive that it has become part and parcel of all the vertical industry. And this trend is going to continue on and on, right? And if you look at how sort of these AI applications, which are very compute intensive and they take a lot of amount of compute resources to not only compute, but also deploy, have emerged across the industry. So if you look at AI finances today, you have large machine learning models that actually do prediction and forecasting in the financial industry. Fraud detection is one of the big use cases which are being used. So AI is being used quite a bit, and this machine learning workloads take a lot of data and being able to sort of predict things in a split-second time. So that has sort of permeated in the AI finance undeniably. Smart transportation has completely revolutionized the whole computer vision, the ability for the autonomous driving vehicles, and the usage of drones in this particular industry today is very much driven by the computer vision models that can detect and classify images, not only at scale, but instantaneously. And those require model training over a period of sometimes hours, days, and even months for models to be trained in a very distributed fashion. I would argue that sort of machine learning workloads have also revolutionized how people are doing work in AI industry as well. I mean, if you look at, for example, radiology, and if you look at how the machine learning or computer vision is actually being used to detect diseases by just looking at x-rays, or they can sort of guide the people based on whether somebody is going to have a heart attack or somebody is going to be subject to any of these diseases based on the amount of data they have collected over a period of years. If you go to the manufacturing, it has completely revolutionized. All the robotics are doing that. And all that's because of the fact that we can actually now have large amounts of data that we can actually do compute, and we can deploy this model at scale. And the hotel industry has now all the recommendation engines, right? If you go to Netflix today, it probably will know whether you're going to like this particular movie, or if you watch Game of Thrones, then you might like Outlander, or if you watch this particular thing, you might like that. That's all done through the recommendation engine, which actually churn through lots of data to figure out who is going to be liking what. And obviously the gaming industry has completely changed, where reinforcement learning is being used to simulate massive games and scenarios and gives you an immersive experience in doing that. All that is because of the fact that now you can actually crunch data at scale. You can actually use these frameworks to give a very immersive experience, and that has somehow become very pervasive. So that's reason number one. The second reason is that distributed machine learning has become a necessity, as I claimed earlier. It's not going to be an exception. And we only have to look at how the trends have evolved in the last 10 years. So if you look at this particular paper, it was published by OpenAI, there's sort of two quadrants here, right? The one quadrant on the left side is the emergence of the deep learning era, where computer vision and neural networks are actually used to compute these. And these are proportional to how much compute time and how much compute fetaflops you actually need to be able to compute something and build a particular model. And then if you go to the further right, this is sort of the advanced large scale era, where now we have language processing model like GP3 and all transformers, which take a fair amount of time to train it, but they give you this great ability to translate things, to compute sentences, to recognize languages, to do translations. All that now has sort of emerged. And this has, because of the fact that if you look at how, as I said earlier, the emergence of AI training models over a period of years, you will see that the scale is not linear, right? So you got all these models which take enormous amount of time, an enormous amount of compute flops to do that, and they increase by 35% every 18 months. And the CPU is just not there to be able to catch up with that. In other words, even if you actually had hardware demand like GPUs, there is still an enormous gap. There's still an enormous gap to actually fill in. And then we feel that the only way you can actually do this massive computing is to actually sort of scale out, right? Which was, again, my original claim that cloud computing and distributed computing is now going in an era where you just distribute at a massive scale, and you have no other way but distribute in that particular manner. So that's sort of, claim number two, or that's an observation number two, or that's train number two that has sort of led to the original creators of Ray to think about, we actually need to create a platform or a framework that allows us to do number one and number two. Now, the third part is that distributed systems, as you saw over the years, it's not easy, right? And distributed programming, for those of you who might be familiar with it, it's not easy, although it's not a piece of cake. It is notoriously hard, and you need, distributed engineers, or you need people who are very deeply in the system engineering to really understand and stitch those things together. And normally, if you were to look at in this two-dimensional lens of the ease of development, whereby you use distributed systems to do massive build machine learning models, or you look at the generality on the horizontal scale, and somewhere in the medium, you have a happy medium. And today, a lot of people are actually using happy medium to do that, which is you stitch things together, right? You pick up, one framework such as MPI, you pick up Kafka or Spark to do your streaming or ETL, or you use Flink, and you use Hortonworks to your distributed system, or you use TensorFlow to do that. That's sort of stitching together. This is the general trend, which is sort of a happy medium. But there are trade-offs, right? Everything is trade-offs in life, right? It's hard to develop because you require a bit of system expertise. They're hard to deploy because of the fact that these are bespoke systems, and they have different communication protocols that might be implemented in a different language. So it's quite cumbersome to be able to actually sort of harmoniously make them work in a manner that gives you this production satisfiability that if I just deploy this thing, it's just going to work. You just have to manage it. You have to be monitor them. You have to just make sure. So it's a happy medium. People are using it. A lot of people are using these, what I call stitching together. If you go to the far right, where it's very general, right? You don't have to worry about anything. You start from a clean slate. I said, okay, I'm a big enterprise. I have lots of deep knowledge about the best SRE system reliability engineers that I can get from Google and Amazon, anywhere, and I can just build things from ground up, where I take my Kubernetes and I take my Docker containers and I just slap them together and I put all my applications on it, and I can just manage it myself. You can do it, right? It's very general. You can just pretty much build anything you want, but it takes time. And it takes very specialized people. And as a result of that, it can actually be quite expensive. And if you look at the far left, right, if you look at the far left in terms of the ease of use, where you don't have to worry about anything, it's just whole about idea of serverless computing that I talked about earlier, where I just write a particular piece of code that I actually want to do some computation. And I just submit it on the server and let the server figure out, how much compute time I need to do, and how much work I need to do, and how much resources that I need to do, and then let it do that. Now, those also have some sort of limitations. One is that they're very cloud specific, so that you might not have everything you actually need for that particular cloud. They're stateless, which means that if you have some certain compute that you're actually working on certain data set, that requires some sort of persistence, where you actually might need the results of that compute later on. You don't have the ability to do that with the serverless computing, because they write or manage things in the memory. And as soon as the server goes down, as soon as your compute is over, scaling down happens and you lose that, right? They might not have the appropriate GPU, the hardware that you actually need to do some computing. So you're beholden to what the cloud provider provides you. And there's sometimes a run limit of how long you can actually have your compute run. So these are all the different sort of trade-offs that you have to general. But how does Ray fit in? How can Ray actually alleviate this particular problem. And so you don't have to worry about choosing the trade-offs, but rather do that. And that's why sort of Ray sort of fits into the idea of saying we want to be able to actually make distributed computing very easy, not only for the developer, but anybody who actually just want to build the infrastructure for running the large, massive workloads to be able to use Ray, right? And so the idea is very simple. The premise is very simple. As I stated earlier, right, the observation by Eric Jonas in the Berkeley lab was that people were just typing things on their laptop. They were just using their frameworks on the laptop, and they're doing machine learning on the laptop. And once they're ready, they actually wanted to somehow, attach to a particular cluster. And so that was the new paradigm that people actually wanted to use it. And what resulted out of this was, well, you can actually take your same applications which you're learning on Python, whether you're using scikit-learn to your machine learning, whether you're using TensorFlow, whether you're using PyTorch to run on your particular laptop. And when you're ready to be able to scale it, you can Rayify it and run it serverless on the computer, and let Ray figure out everything you actually want. Let Ray figure out how many clusters you need. Let it figure out, distribute all your code. Let it figure out how fault tolerant you got. Let it figure out when to bring down the cluster, when to scale out the cluster if you actually need superpower. And that was what people actually wanted to do. In other words, they wanted to have the same experience that they are working on the laptop as they would actually on the cluster. There's no seamless, just the same code changes. They might just have to change 1 or 2 lines of code to be able to connect now to a particular server. And so that was the sort of the vision of particular Ray, and that's how it actually fits in. And if you actually look at Ray in the grand scheme of things, at a very high level, as I say, is that it is a layered cake of capabilities and computational functionalities, right? It can run anywhere, right? Ray today can sort of run on any of the public clouds which are available, as well as on your laptop, and as well as on-prem. So that gives the flexibility of anybody who actually wants to take the advantage of Ray to run on any of this public cloud and any of the architectures which is actually needed. If you go up the stack a little bit, you have the core of Ray, which is a universal framework for doing distributed computing. What I mean by universal framework over here. In other words, Ray sort of provides you the ability to give you very early low-level primitives that you can actually build things on top of that. Now, those of you who actually have sort of studied the emergence of how systems are actually built from ground up, and the best example I can give is Unix. If you look at Unix and Linux, how it actually evolved, which became a standard today for a platform to run all the application, is because it was built in a very modular fashion, where we gave people low-level primitives to build things upon. Think about Lego blocks, right? Lego blocks are little blocks that you actually use to build things on top of that. So the whole idea behind this was that we're going to give you a few primitives for you to actually build things on top of that, and then you can actually build whatever you want as a framework. And so if you go up the stack a little bit, you have this entire array of native libraries which are actually built on top of Ray using the primitives, so you can scale things out. And then the integration of all these very popular machine learning ecosystem libraries that exist today, which are integrated with Ray. And if you happen to be someone who just wants to build your own particular framework, you can actually use these Ray primitives to build your own framework, and then use Ray as a compute strat to do the scaling. So that is sort of what I would call the layered cake of functionality and capabilities in the Ray ecosystem. And those collectively address the 3 things I talked about. One was that today machine learning is very pervasive, and people are using all these particular frameworks to build this. And in order for you to take advantage of the scaling, because you actually need for that particular scale, which is the second thing, you need something similar to like that. And the third thing is that writing and building distributed computing is difficult, but if you actually have an infrastructure that seamlessly allows you to do that, and you just write your Python code as if you're writing on your laptop, and then when you're ready, you just say, connect to my cluster, and then now it actually runs on the cluster automatically. That is really where things are actually heading today. So I'm going to pause here for a minute or a second to see if you have any questions. I talked a lot about. Any questions?
So you mentioned that Ray is both online and you can use it on a laptop. Is that correct?
Mm-hmm.
And what would be the difference between the two?
Good. So the question is that sometimes, remember when I said earlier in one of the slides, is that people want to be able to run things on the laptop to try things out. And if it doesn't fit everything, for example, the data is too big or the compute, today's laptop for about my Apple laptop has got 12 cores. That's a lot of money. That's a lot of cores on it. But somehow I'm building a large AI computer vision model, and somehow 12 cores are not enough. It takes about 3 hours to train my model. I'm going to now use a Ray cluster, right? So I distribute my load over. So the question to answer your question is that when you want to try things locally, just to play around with this, you try running things locally on the Ray. So you will distribute your workload across all the 12 cores on your laptop. But if you realize that that's not sufficient, or you need GPUs to do some computation and you don't have GPUs on the laptop, you attach now to the Ray cluster, and it will now use the GPUs to do that, and it will distribute the load over there. So the fundamental difference is that you try something on your laptop, you work, you're happy with it. Now you want to scale things out with a larger data set, you now use the Ray cluster. Does that answer your question?
Yes, sir. Thank you.
You're welcome.
Anything
else?
Yeah.
Yes.
So earlier in one of your slides, I was curious, you're talking about how the apps are increasingly incorporating AI. Most of those smart transportation and gaming to name a few. I'm curious, so as you explained, essentially you're using the architecture to scale processing of data when you can't do it locally because it takes so much time.
Right.
What is the I'm curious to see if there is something about a workaround in those scenarios where latency or the distribution between data and the cloud server and coming to something like AI in a vehicle that has to constantly learn and rethink and re-update, how that would affect in day-to-day life.
Good question. I think that's a very general question. This is what we call deploying AI models and machine learning at the edge, right? Now, edge over here is that yesterday I was taking a ride in Tesla and I was quite immersed by looking at this massive monitor. It was the first time ever I've gone into a Tesla, and I was looking at how the LiDAR system was detecting images, and all this actually happening in real time on that particular machine. So what I'm talking, there are two things over here you're referring. What was your name?
Hugh.
Hugh. There are two things. One is inferencing in real time, and the other one is training, right? The training of the particular model is where you actually need the distributed computing, not necessarily inference. Sometimes the inference is very fast because you only train the model, and the model itself is not that big. You just have weights and biases that are needed. The inference just happen in real time. It doesn't have to go to the mothership to find out what the inference is. In some cases, but in most of the cases that you're referring to, is happening in real time. So you train the particular model using the cluster, and now you're actually deploying it on the edge device, and that's where the embedded system comes in. The question about the real-time learning is that what happens now, I haven't seen this particular data, right? And I need to retrain the particular model. And this is where now things get triggered on an alert system where it's saying, I just found out something that I haven't seen before. I need to retrain them. This is what we call real-time retraining. And we are sort of entering in particular phase of doing real-time training, because right now, the way you actually do is that you will actually retrain the particular model and redeploy it. But the real-time distributed training is still sort of emerging field where you don't have the resources on the Tesla to do the massive retraining of data, but you would do it on the mothership and then download the particular model and update that.
Got it. Okay, that makes sense.
Anything else? Okay, so the next thing I want to talk about, the Ray sort of unifies distributed workloads, right? And in my earlier slide, I talked about how the libraries are built on top of Ray as an infrastructure so that you can actually use the workloads that you need to distribute. Now, what are some of the workloads in AI? Right? What are some of the workloads in machine learning? This is where these native libraries come into play. Now, some of the workloads are, you might be, for example, doing data processing, right? You might be having a large amount of data that you need to pre-process before you feed into the machine learning language. Now, you can actually do that using the Ray datasets, which is the library that allows you to do last mile ingestion. Now, don't confuse data processing over here with doing the ETL or doing massive amount of pre-processing using things like Spark, right? Ray comes into the picture where you have actually figured out your data story. All your data that exists has been cleaned, has been sitting in the lake house, and now you're actually ready to ingest into machine learning that actually do that. Now, you might have some last minute pre-processing that you actually might want to do. For example, you have data in certain way, but you now want to feed into your deep learning model, you want to convert that into tensors, or you want to normalize the data, or you want to use scalar algorithm. This is where you can actually use Ray datasets. So there are different libraries. You can actually use what we call modern, which is like pandas in a distributed manner. You can use Mars, which is the distributed library to compute tensors, right? So if you're using deep learning, tensors is the data structure in how it actually understands and does the computation. There's Dask, that you can actually use Dask on Ray. So data processing is sort of one workload, and data ingestion is one workload that allows you to scale your AI workloads. And this is when you're doing training. The other workload is very common today to build the model before you deploy that is training, right? You want to train those models, and you can train those in a distributed fashion so that you actually now can scale across a horizontal cluster where everybody gets a copy of the data and works on the same model to create that particular training function. You can actually use PyTorch, you can use scikit-learn, you can use Hugging Face or Hortonworks to do your training in a distributed manner, or you can actually do that on a single machine. So those are sort of the workloads that you have to scale on a particular cluster. After you have actually done your training, what do you want to do? You want to deploy this model. And as Hugh pointed out earlier, how do you deploy models on the edge, or how do you deploy a model on your website or on a cluster? And this is where the serving part of the Ray comes into function, where you actually now deploying your models that you actually built and deploying it in a cluster or on a website or on a production server where people can now infer, people can actually score. So if you have a fraud detection model that you have built that took massive amounts of data and now is generalized enough to be able confident that I can deploy this in my financial system and I'll be able to predict something that's fraud, or I can give a classification whether this loan is going to be approved or this loan is going to be rejected, or I have this image that is going to classify this as X or Y. I'm now going to serve that product. I'm going to deploy it. So Ray serving is another library that allows you to do that. But I think more important that all these work together or can work independently. You don't have to use the entire thing. You can use one or the other. It's not like one or all. You can use selectively those things. And hyperparameter tuning, for those who are not familiar with, is the ability to tune your model so that you can actually choose the best hyperparameters that will give you the best model, right? So the instance of a hyperparameter tuning, for example, if you're doing XGBoost machine learning model, you need hyperparameters. How deep my model is going to be, how many trees to use, right? What is going to be my split factor? How many jobs do I actually want to run? All those, or if you're building a deep learning model where you're building a neural network, you probably want to somehow figure out what is the best architecture that's going to define my computer vision model. How many convolution dense layers do I need? What are going to be my filters? How much is going to be the size of the filter? What are my initial weights? What is going to be my learning rate? Am I going to drop out certain bad trials? All this is part of hyperparameter tuning, where you're actually experimenting all these different parameters over a large hyperparameter space, so that it exhaustively and selectively and intelligently goes through different configurations to give you the best model. And that's called hyperparameter tuning. And the other workloads, which are very, very common that people actually scale at massive scale, is reinforcement learning. And reinforcement learning is actually being used quite a bit today, both in simulating models about real life scenarios, or building recommendation systems, or in the gaming industry where you actually build these agents and models that actually simulate your playing model. So these are what we call, the batteries included library as part of the array. And together or selectively or independently, you can actually use one, or you can use the composability of these. And these allow developers of flexibility to use those together to build their machine learning at scale. And so, don't take my word. These are some of the customers, these are some of the companies who are using Ray at a massive scale, right? You got the Amazon who are actually using terabytes of data to do the pre-processing to build the particular models. You got Uber of the world who are actually using Hortonworks and distributed training to build all these particular models and then deploy that. You got McKinsey who actually built the America's Cup using the RL library to build the simulation of the America's Cup library to get the best hydrofoil simulation model for the boat, so that when they actually run this particular boat and create this particular boat, that's going to be the best boat that will give them the best efficiency and less friction in when they're scaling through the waves. And that eventually, using this particular technology, were able to win the America's Cup. You got Ant Group who are using over 200,000 cores using Ray to produce good. Alibaba is another one. So all these companies are actually using Ray at a massive scale. And so you don't have to believe me, you just have to look at their website and see how they're actually using Ray. And all these different companies use these different workloads that I talked about for doing their independent data processing. So Amazon is using a lot of data processing for doing task on Ray to do the pre-processing, to use data sets for that. Uber is actually using training for that. Wildlife uses the model serving to deploy this particular model. Dendra has done an incredible job in doing hyperparameter tuning and using the computer vision to have drones that actually run across deforestation areas. It's sort of one of the most interesting use cases I've seen, where they actually use the computer vision to figure out in the deforestation area where they can actually keep track of the plants that are. So your drones go out and they inject in the barren land seeds to refurnish the forest, and they keep track of how through taking images from the drone to tune those particular models to make sure that they haven't escaped any part of that. So that sort of Dendra, and obviously Shopify uses that for recommendation system. So all these companies are using all these different models to scale this at a massive scale that actually require. And you can actually see how these, you can actually read about, the technical details if you're actually interested to find out how these are done through this particular blog. And I'm just going to skip over this very quickly because I think we're running out of time. This is a typical sort of, this is a bit more technical. This is what a cluster looks like. It's very unique to Ray because it is a very distributed system. Unlike any other systems you actually used, it uses this in a very distributed manner. That's quite unique to Ray. And there are what I would call distributed design patterns and APIs. Now, before I actually get into that, I'm just going to pause here to see if you have any questions.
Jules, can I ask a question here?
Yes, yes.
Cool. I teach the PySpark and machine learning. And so many of students here already know how to build the training and testing of PySpark machine learning. And what is the difference or strengths of Ray to do the kind of same thing, or especially with the deep learning and GPU, etc.?
So I think the general broad question is what's the difference between how Spark is, what is Spark strengths and what are the Ray strengths? And to give you a very simple example, if my grandmother would ask me this particular question, what's the difference between Spark and Ray, I would say, Grandma, you got two grandchildren. One is Jules and the other one is Julie. Jules is very good at doing things that Julie isn't. And then Julie is very good at doing things that Jules isn't. Now, if I were to answer your question to an engineer or to a data analyst or to a person who's going to be a product manager in this new era, what's the difference? The difference is a couple of things. One is, by default, by de facto, there is no question in this world, Apache Spark is the de facto engine to do distributed data systems, right? Now, distributed ETL. If you're doing distributed ETL, if you're doing SQL workloads, if you're actually doing streaming processing, I would not think of anything else but Spark. And I would not think of anybody else but my former great employer, Databricks. I would actually use those platforms without a beat. The difference is that Spark is has a status scheduler. So what Spark does, it does what I would call lazy evaluation. So when you actually, for example, when you actually create a Spark ETL job, or if you create a Spark query in a data frame, you're going to have all these different methods that you actually going to create. And the way Spark does that, it actually goes through the transformation of creating each and every, in a particular DAG. And then when you create an action, it executes that. So it lazily evaluates that thing, right? So that's one thing. The other difference is that Spark and Dask is built on what I call a data abstraction, such as data frames or Dask data frames, and on which an entire DSL is actually built. This is completely different from Ray. Ray is built not on anybody that's abstraction. Ray is built on the fact that we're going to give you this primitive and design patterns, and then you use this design patterns to do whatever you actually want. It has a distributed schedule, which means that there's no one driver that runs everything. Any worker can actually create a particular job and create that. And it is done eagerly, which means that you create your execution and it executes right away. And the reason you need that eager execution is because in certain machine learning frameworks, you need to be able to, when you're doing tuning, you need the ability to get the result of the previous operation right away to decide what my next trial is going to be. And that has to be sort of done in an eager fashion. And then the other one is that Ray actually uses what we call distributed object store. So you have a distributed object store across the entire cluster, and any data that's actually created by a function or a compute that runs on the store, you can actually get access to that. Now, if your processes are running on the same machine, then you can actually use shared memory to get your zero copy efficiency. So there is that particular difference. So those are sort of fundamental difference. And then, as you pointed out, scaling, right? The ability to actually use GPU and the support for deep learning models is far more favorable in Ray, because that's what it's actually built for. Whereas Spark has the best de facto data engine today to do your analytics and to do your ETL or ELT, to build your data lake, to build your Delta source. Once you've actually built all that, now you actually want to take all the data and put it to use by using Ray to get this particular data and do massive parallel computing or parallel deep learning training at scale. So I think those are actually fundamentals, and they're very complementary, right? They're extremely complementary, they work well. And I see in the future that both systems are going to be used together, where Spark does all this enormous amount of data processing, massive scale, to build your massive delta lakes and lake houses. And then once your data is over there, you can actually now use Ray to bring all the data out and do distributed training or learning or tuning or whatever you actually want. So those are sort of both complementaries and contrast. Does that answer your question, Jongwook?
Yeah, exactly. But so there is like a benchmark that shows Ray's, for example, deep learning and the PySpark's machine learning result. I mean, comparing those kind of things, or
they are. I mean, we have released some benchmarks on our documentation where actually talks about how Dask on Ray is faster than running Dask by itself. There are some independent benchmarks written by Ent where they run Spark on top of Ray, right? There's Spark on Ray project where they've seen that. But no, we actually haven't published any because we don't see them as competitors, right? We see them very complementary. So it's up to you whether you actually want to use one or the other, right? But there are certain deep learning models which scale very efficiently on the Ray compute cluster.
Thank you.
Mm-hmm. Anything else? Okay, so quickly, I just want to talk about design patterns because I think that's the core of what Ray is. And design patterns are not something new. You know, design pattern was sort of introduced earlier for those who are software engineers who come from the particular background. Is a way of doing things, right? And Ray sort of depends on these three design patterns, which are, you know, taking a Ray task or taking your Python function and converting into a parallel task, or taking your Ray objects as features. And one of the things that Ray does very efficiently is that when you send a compute to a particular Ray cluster, you get back the result right away. Now, the result is not ready. What you actually get back is the handle to the future. And at some point, you'll be able to get that particular future and query that, what's the status of that. As a result of that, you can submit tens and thousands of tasks, and you get things are sort of running in parallel. When they're finished, you can query them in a manner to get the results back. And then the other idea about what we call Ray actors. And Ray actors are, think of it, Ray actors as stateful operations or stateful parallel tasks that you can actually now maintain and keep state of things that actually change. And those are sort of what we call Ray actors. And there's some other design patterns that actually exist. And just very quickly, you know, for technical folks who are out there, you know, you take a Python function, you convert into a task, and now that task is running on a particular node. You take a particular class that you actually have a Python class, create an actor, and now you can actually run that as an actor, as a microservice running on your Ray cluster, and you can sort of, you know, send queries to it and update any internal state it actually keeps. And Ray actors are very fundamental design pattern on which all these other libraries are built, because you can actually build very sophisticated microservices using Ray actors. And as I mentioned, Ray actually uses what we call an immutable distributed object store, where any function that actually creates a particular object is now stored in a distributed manner on the particular shared memory. So any other process that actually needs the data, if it's running on the same machine, it can just do quick zero copy because it's running on shared memory. Or if it's on another cluster, we can just make quick gRPC call and copy it over. And now you actually have multiple copies of those running, and it's very efficient to be able to do that. Here's a very simple code. Obviously, no Ray lecture would be devoid of a code. It's very easy to take your Python function and just decorate that with those two parameters, Ray remote, and now this function now becomes a Ray task. Or if you have a class, you can just decorate that with the Ray remote. And if somehow your counter requires that it's doing some GPU computation on a graphic image, then you can say, I want number of GPUs to be allocated is 1. And the way you invoke those remotely is just name of the function and the name of the file, and then returns you an inference or returns you what I call a future. And then you can pass features anywhere you actually want on the cluster, and you'll figure out, oh, this feature is being computed over here, so I'm going to get the particular data from there. And when you do array.get, it just returns you back the results. And same thing when you want to use your actor, you can actually use counter.remote to actually execute that. So this is where sort of, the APIs are being used by the people who actually want to write distributed computers. And what is it the developers actually want, right? What developers really want, as what Hugh pointed out earlier, and I think somebody else asked me, I think it was probably Marcos who asked me, what's the difference between running something on a laptop and what is it the difference? And I think today the trend is that people want to develop things on the laptop. Right, I do everything on my laptop. When I'm ready to do something that I actually need a larger data scale, or I need a massive amount of data to do some more training, then I'll sort of use the cluster. And this has been sort of the paradigm that's going to be emerged, and a lot of engineers and a lot of data scientists are sort of using that. I just want to use my laptop right now. I'm going to pip install things on it. I'm going to run it for a while. When I'm ready, I'm going to create a Ray cluster. I just attach to it and then let it run on the server. And then the production side is something else. But this is sort of the new way of doing things. And sometimes it's a huge barrier because you have to figure out what your local environment is going to look like. Can actually reproduce that on a cluster environment. And one of the things that Ray and Anyscale allows you to do is that you can actually have your local environment look exactly the same as the one of the staging environment by just saying, here are the things that I need, my dependency, and you will have those available over there. So your code running on a laptop, for for its dependencies is not different from what's actually running on the cluster. And that's actually a powerful barrier. It used to be a huge barrier because the system administrator have to SSH into the particular machine remotely and then make sure you have all the right dependencies. Whereas over here, Ray sort of takes care of it by you just telling me these are the things I need, and it will just figure out for itself or install things for you, and then you can actually run those seamlessly. And this is sort of gives the developers today and the future of how you can actually scale your AI applications, AI workloads by using things, doing development on your laptop, and then connecting to an Anyscale that provides you a managed service array cluster. You don't have to worry about managing all that. It just automatically auto scales and auto scales down your production or your staging server. So that essentially is the essence of what I talked about in other ways. And the takeaway as a distributed computing is a necessity, not a norm. Ray's vision, as I said, is to make distributed computing programming simple, to be able to scale that workloads with Ray libraries. And Anyscale is a way that actually gives you the managed service of Ray, so you don't have to do it. And there's this notion of infinite resources available because, well, infinite over here, I mean within the physical norms of what's available, but you can actually scale out and scale down as you need the resources while you're training or where you're inferencing. So that essentially is my today's talk. I just want to make sure that I share this with you, where if you want to start running and about Ray, pip install Ray. We have tons and tons of documentation. I have loads of code examples and reference guides. Join our meetup, right? We're having a meetup on monthly basis. Join our forum Slack channel and follow us on social media so you get updates on what's actually happening in the distributed world, particularly with Ray. And a couple of announcements. Those of you will be using Ray or are planning to use Ray currently and want to use Ray, we actually have our first in-person summit happening on August the 23rd. The CFPs for those things are open. Jongwook, make sure you submit something. We actually have different kinds of talks, lightning talks, 30-minute session, deep dive. So hoping to see your name on there.
My pleasure.
Yeah, I'm on the committee, so I'll make sure that it gets somewhere. And we also have reinforcement learning. Those who are interested to find out what RL is all about, how people are actually using production. We actually have a Ray Summit happening on March the 29th. It's virtual, it's free. You really get to hear from people who are actually in the industries who are using reinforcement learning. What are they actually using for? What problems they're actually solving? So this is actually a great opportunity to expand your knowledge about how reinforcement learning today is becoming an imperative workload in machine learning. And if you're more adventurous, in the afternoon session, there is a paid tutorial. I've created this particular code called rlsummit.com. If you actually use that code, you can actually get a discount. And thank you very much. It was a pleasure to share this knowledge with you. You can get in touch with me, send an email, whatever you want. Connect me on LinkedIn. Just tell me you attend this lecture so I know who you are. And just follow me on Twitter and I'll follow you. I know it sounds a bit dodgy, but that's how it is. So I'll just sort of end this and thank Jongwook for inviting me, and thanks all of you for paying attention for my afternoon. I hope that if this was an evening talk, this would have been probably a cure to your insomnia, but I hope that you're not suffering from that. So I'll answer any questions you might have.
Oh, thank you for your great introduction of cutting edge technology, and very interesting. I know you have a very busy schedule today, and you can still accept several questions, right?
Oh yeah.
Okay.
Oh yeah. I mean, I'm Saturdays. All I do is I work, so I consider this part of my work. So yeah, I'm happy to hang around if you have any questions, for sure.
So you guys, it's really hard to meet such a person like Jules, who is at the core of cutting edge technology and a startup like Ray, right? So feel free to ask any question. Louis, you want to have a question?
Yeah, I just have a question. It's kind of just a general question. It really doesn't go depth into the program, but just if someone wants to get into data analytics for a job or a career and they don't have really have any experience, speaking for myself, I don't really have any experience in data analytics, but I do have experience in banking and investments. How would, with your expertise, how would someone be able to get into this industry?
Okay. I mean, if you're a data analyst, I think one of the big workloads today in big data analytics is doing data analysis on your data, right? So what are the languages that I would have to consider? So SQL is something that I would try to master, to understand, to be able to sort of analyze the data, right? Because the first thing you're going to do as a data analyst, if you're going to join, let's say, a data team, and the data team consists of a data analyst, there's a data scientist, there's an ML engineer, or there's a research scientist, and they're all part of a larger data team. In the olden days, there were silos. People would just work very independently. Now the data teams work together because now the volume of data is actually changed. So the data analyst will work with the data scientist to say, okay, I want to build a particular model that will predict, let's say, my inventory on my store. And you as a data analyst will look at all the data that's available for you, and you will make some certain queries, and you create some tables, and you will say, hey, listen, I've looked at this particular data. The trend is showing me this. Is there any way you can actually build a particular model that take this particular data that I've analyzed and I've created, and I think it looks like we might be able to create a particular model that gives us a forecasting or gives us a projection. So as a data analyst, you sort of play that particular role, and the skills you actually require is not necessarily programming, but SQL is what I would call a declarative language, where you tell the SQL how you want to do something. You want to aggregate something, you want to sum something, you want to select something from there, you want to combine those two tables, to join the tables to see what they're common, what are different. So as a data analyst, yeah, I would start with that particular thing. And then, if you enjoy that part of the fact that, oh, I can actually write this SQL code, really cool, then I'll start, learning things like Python, and then go to the next level. So yeah, I mean, don't be shy, don't be intimidated. Data analysis is actually a good way to get into, and then you can actually step up to be a data scientist, or if you want to sort of get into deep learning and all that, then you take some other classes. But yeah, I would take that route.
Thank you so much.
You're welcome.
Anyone else, feel free to ask a question. Hugh, you also have a question?
Wait, I think somebody was before me, maybe. Oh, okay. Never mind. Yes, I have another question. I don't know how long this question could potentially go on, or like the questions. I'm just very curious about this, and I apologize.
No, there's no apology. Curiosity is what drives people forward.
Thank you, appreciate it. So I when it comes to all these complex things, I don't know much about it, but because I'm a nerd at heart, and I grew up building computers, playing games, and all that fun stuff, I tend to take it and like gamify it. And so as you were talking about Ray, I understand that the main premise of Ray is as a scheduler that decides the fate of how the data is consumed, essentially. You can say I'm wrong, that's fine, I accept it. But when it comes to things like video games, I think of like ray tracing, which is the newest thing, which coincidentally is a similar name. But I was thinking about how the process works, and how essentially it takes all the data collected from the game, takes it, and breaks up into chunks to determine the physics for lighting. And so knowing that, there is a strong emphasis on the scheduler and how that is processed, and the limitations we have currently now in terms of just small scale gaming is that the processing speed is affected by the API from the developer, but then also by the raw data that can be crunched in the GPU. And now you're scaling that 100,000 times in a giant supercomputer. Is there a potential for that to be a limitation for the scaling of Ray, since it's taking that data versus Spark, which is just a large diesel truck that just knows how to pull things from one point to another? trying to figure out an effective way to approach a data set and convert it, for various applications. Is that an inherent limitation of Ray?
Well, the only inherent limitation of any data processing, including whether it's Spark or Ray or Dask or Hadoop, God forbid, is the physical limitation of physics, right? So to answer your question about the fate of data is not determined by the scheduler. The fate of where your compute is going to run is determined by scheduler, because the data is going to be distributed and available to you anywhere in the particular cluster.
Okay.
Where you actually schedule your compute is more determined by the distributed scheduler, by saying, okay, this particular resources require GPU, right? This function who's actually doing ray tracing is a heavy mathematical computation because it does all the mathematicals, does all the metrics computation. And I'm not going to schedule that task on a cluster that has got 24 CPUs, but I'll schedule that cluster on a cluster that actually has 12 GPUs and limited CPUs, because I need to do metrics computation, I need to do ray tracing. So that's how the fate of the compute rather than data is determined at Ray. In terms of how the modeling is actually used and how it applies to how gaming is actually done, Hugh, I would implore you that you join the RL Summit, because one of the main speakers from Riot Games, and he's going to be talking about, obviously how reinforcement learning is being actually used. But if you look at Riot Games, what do they do?
Oh, they make, well, at this point, they do a little bit of everything, but
yeah, but gaming is
games.
Right. So gaming is a big thing, right? And reinforcement learning is a huge component in how you actually use the data, right? Because reinforcement learning is you actually create an agent interacts with that environment, and then based on that environment, if the agent does the right thing, then they get reinforced. So next time the agent, well, I'm personifying the agent, but the agent is just a program that's running, that's looking at the environment and interacting and learning things as they actually go along, right? So there's no limitations of that. The limitation is only, the underlying hardware that I have. And as I showed in that particular graph, the amount of hardware now scaling, where, for example, with NVIDIA CUDA libraries available, you can actually do a fairly good amount of computation. They're dedicated hardwares which are just used for these kinds of things. And then if you just want to use that as part of the array, you can actually use that. So there's no limitations per se. Limitations is only limited by what physics allows us to do in cloud computing, right?
Okay.
But I would urge you to attend that summit. Just sign up for it, because you will really hear from the horse's mouth, right? And it's not only in the gaming industry, right? Because we have people from Dow Jones and we have people from Berkeley who's going to talk about how reinforcement learning is actually being used in the real world. And there are people from across all industries, right? How recommendation engines are actually built today, right? Using all this particular data that you have, that you go to a particular Shopify store or Amazon and they say, Jongwook ordered this thing, you are connected with Jongwook, he'd like this, so that's what you would like it too. All these kinds of things happen. You wonder how they actually figure that out.
Okay, cool. Thank you. I appreciate it.
Jules, also, majority of participants here are MBA students. So they have expertise in their business domain.
Oh, definitely.
Yeah, so if you introduce a simple a user case that has, for example, company A has some data issues, data or computing issues, so they had to use like array. So do you have some kind of example why?
Yeah, I mean, if you look at Shopify, for example, right, the number of use cases that actually showed what companies are using what for, right? Take an example of Shopify, or take an example of Ikigai. Let's take an example of Shopify. Well, they had all this amount of data, right? They already used, whatever ETL engine they used to put all the structured data in let's say, S3 or some modern data lake that they have. Let's assume for argument's sake, they use Delta Lake. So you got all this purchase structured data. Now they have a use case. They want to figure out how am I going to build my recommendation engine for people who actually come in to buy certain things. And if they bought certain things, what historical data they then actually use, what are the features that I can use, who are they actually connected to, that I can actually exploit that and recommend them. Maybe they should buy this because in the past you bought this particular item and it's very much related to what we call search entity relation, where this item looks very similar to this in terms of features. So I'm going to go ahead and put that image over there. So those are the business use cases that a product manager who is going to be either from the School of MBA along with a little bit of computing knowledge says to the data scientists that I think we should actually build a use case model where we can actually build recommendation engines. Another use case is fraud detection, right? You are working for a financial company and you are assigned with this new task of you've created a new online evaluation system where you can actually within instant 5 minutes or 2 minutes go ahead and make a prediction whether this particular loan application will fail or will default or will pay in a timely manner. You as a business person, as a product manager, are given the task to figure out how you're going to build that application. And so you're going to actually create all the data that's available for you to somehow work with the data scientists to say, can we actually build a prediction model that given these set of parameters without any bias involved in it, where we can actually predict, right? Where your loan is going to be approved. And those are use cases, for example, if those of you who are familiar with some of the applications as part of the WeChat, right, that actually have a loan application. I can put 4 or 5 parameters on my WeChat application and within instantly, within 5 seconds or 20 seconds, I will get an answer where your loan is getting approved or not, right? So that would be sort of another use case. So I mean, those are the two things that I see being prevalently actually used. And there are other use cases where you might want to detect something, or for example, Dendra is, I gave you one example, but the other ones are sort of more complicated because they require deep learning knowledge. But for fraud detection and for forecasting is another use case, right? You're working at a clothing store and you have all this data available in all the different items that you have available in the store. What is your forecasting model? What are you actually predicting based on season? How much should we order? How much should be disorder? What is the forecasting? So that would be another use case in which you can actually use Ray, right, to predict something. And you can actually, if you have lots of data, you can actually use deep learning models to do time series analysis, right? And time series analysis is very common in the financial world.
Thank you,
Those are the use cases. Yeah.
Sure. There is a Melissa who wants to ask a question. So Melissa,
Go ahead, Melissa.
Yes, hello, thank you. I was wondering, so you mentioned a lot about bigger companies and how larger companies are able to use Ray. What about like smaller companies, including like a small manufacturing that maybe just, or like specialty manufacturers? How could they use this system if it's even for them?
Yeah, I mean, that's actually a good question, right? And the same question would actually would apply to, if I'm a small company and my data set is really small and I'm just, using, very small data that actually fits on my computer, there's no need to use Spark to do that, or there's no need to use Ray because you're not dealing with scale, right? And the whole premise of Ray is to be able to scale those things. So if you're a small company and your data size is small enough to fit on your laptop or on one single EC2 instance on let's say Azure or EC2 on AWS, then do you actually have to use Ray? It's up to you. It's not a necessity, but it might help you to crunch things faster if you have a large machine and you have your data sets. But the thing to consider is that you might start out small, but 2 years from now, Melissa, or 5 years from now, Melissa, if you hit the jackpot, your company is going to grow and the amount of data is going to grow. So it's nice to actually think about long term when you say, okay, I know that 5 years from now, the amount of data that I'm going to collect for manufacturing is going to be large. So I'm going to start first with small. And then as I start needing more compute resources and as start needing more data storage, I'm going to start scaling. And as I said earlier, the trend now is cloud computing where I'm going to do serverless, right? So you, as a data analyst or a data scientist working for the manufacturing company, you don't need to worry about how big my cluster is going to be or how small my cluster is going to be. I'm going to be able to write my particular small program and I'll run it to do my computation, and I'll just pay for the amount of resources that I used on AWS, for the amount of resources that I used on Azure, or the amount of resources I use on GCP. So that's the whole idea behind serverless computing, where you don't have to worry about, oh, I'm going to make sure that I only create one cluster that has the smallest node. I think that idea is actually gone now, where serverless computing become more and more way of saying, I'm just going to, write this particular job and submit it. And if that happens to be Array, then Array will figure out, how many clusters you need. And you only get charged for the CPU that you use or the GPU that you will use to do your manufacturing computation. If you were doing any robotic computation to do the detection of some visual objects, or if it's just number crunching for forecasting, then you just use CPUs to do that. And you will only use and be charged for the storage that you use and for the compute resources, not for the machine itself.
Thank you so much. That was very helpful.
All right. You're welcome, Melissa.
Jules, I think the time is moving quickly, and I'm pretty sure there are students who wants to join, for example, your company. You guys are recruiting. If you are, then do you have any contact point here?
Well, we are always looking, right? We are a growing company. We are close to about 100 people now. Yes, we're looking for all kinds of people. We're looking for project managers. We're looking for engineers. We're looking for marketing. We're looking for sales. We're looking for all kinds of skill sets. And if you're an MBA student and you're getting out and you want to learn about how to be a product manager, we have internships as well. If you're still in school, so look at our website. Go to jobs website and see what job description fits. And there, if you want to do internship, yeah, we do actually have an internship. Right now, the internship is more focused towards engineering, but I think sooner or later, we're going to be opening internships for product managers and for marketing as well, because it's a growing company. And some of the best work I have experienced and I've known comes from interns. They just do an incredible job.
Thank you. So I think it's almost time to wrap up. Any one question that you want to ask at this moment?
No.
And if something pops in your head, feel free to send me an email or connect me on LinkedIn or follow me on Twitter. I'm more than happy to answer your question on DM. I'm there 24/7.
Thanks again, Jules. And please give him big hands. And thank you again, guys.
Thank you.
Right. Go Cal State. Go Cal State.
Yeah.
Thank you,
Thank you so
Jules.
much.
Thank you. You're welcome,
Thank you, sir.
man.
Much
Oh my
appreciated.
Good luck. Good luck to the graduating class.
Thank you.
Great.
Thank you.
Thank you, and
All right.
have a great weekend, Jules.
All right. Cheers. Thanks.
Okay, bye now. And see you guys at the regular Zoom session at 2:30 p.m. Thank you, guys. Bye now.